Hello everyone, my name is Alvaro and I'm going to be showing you how to solve a physics problem from chapter 7. It's called Energy of a System. The main concept here is going to be Hooke's law. Alright, so first things first, you got to make sure you read the problem really carefully. It's problem number 27 on page 194. This is the figure here, and I'm just going to read it to you. You have a freight car that's being stopped by two springs, the smallest one and the bigger one. So let me go ahead and read it. A 6,000 kg freight car rolls along rails with negligible friction. The car is brought to rest by a combination of two coiled springs, as illustrated in the figure. Both springs are described by Hooke's law and have spring constants K1 and K2. K1 is 1600 newton meters and K2 is 34 newton meters. After the first spring compresses a distance of 30 centimeters, the second spring acts with the first to increase the force as additional compression occurs, as shown in the graph. The car comes to rest 50 centimeters after first contacting the two-spring system. Find the car's initial speed. So as you can see from the figure, I don't know if you can see that really well, but here is when it starts to become compressed by the first spring, and 30 meters into compression of the first spring, it starts becoming compressed by the second spring. And as you can see here, as the total force of the spring system increases. So make sure you read the problem carefully. List your knowns. You know the mass of the freight car. Which is 6,000 kg. You know the spring constant of the first spring, which is 16,000 meters. The spring constant of the second spring, which is 3,400 newton meters. And you also know that it goes for the whole system compresses for 50 centimeters. You gotta make sure you convert those units from centimeters into meters. So here I showed you that it's compressed 0.5 meters. So you want to find out the total force acting. Make sure, don't forget to draw your diagrams too. Alright, here's this diagram is before it reaches the spring, this is after. This is when it compresses for 50 meters and it comes to a stop. So here the velocity is 0. And we are solving for the car's initial speed. Let me write that down. See, the initial velocity is an unknown. Final velocity is going to be 0. Alright, so let's get started. Alright, so when it reaches its final velocity, which is 0, you want to find out what are the forces acting on it. You know that right now here, the two forces acting on are going to be the two springs. So you're looking for the net force in the horizontal direction since there's no vertical component. And that's going to be just the sum of your net forces, which will be the sum of the first spring and the sum of the second spring. And I'm just going to write that down for you. Here you go. So your net force should be your net force should be the force of the first spring and plus the force of the second spring. And it's on the horizontal. There is no y component. Now that you solve, once you have solved this, you're gonna, to solve this equation, you're gonna be using the force-static friction. Yeah, you're gonna be using the force-static friction equation to solve for both the different forces. And let me write that equation down for you. Which is just the coefficient of friction times the normal force. Once you've solved for your net force, you can go ahead and start to solve for the hold on. Pause. Okay, so also from the information given, you can also solve for the work done by the spring system, or by both springs since it's two different springs. You're gonna have to find the work of the first spring, and then find the work of the second spring, and then add those up to find your net work. So let's go ahead and do that. You're gonna use your work on spring, which is just looks like this. It's half k x squared initial x minus half k x final squared. There you go. You're gonna do this for both the first spring and the second spring. So your net force should be the sum of the work of the first spring plus the work of the second spring. Right there. That's this. Once you solve for your net force and your work, you can go ahead and solve for your final velocity. So using second second law, you know that F equals ma, and you go ahead and solve for the acceleration. Which is just a equals F over m. You could also use, looking back to chapter 2, you can use your kinematic equations to solve for the final velocity. And you would just, let me show you. So here's our kinematic equation, and we're going to substitute a, since we're going to substitute a here for this a in our kinematic equation. And we already know our force, which is the net force of both springs up here, right here, this equation. Okay, and then you could just solve for your final velocity right now. Excuse me, your initial velocity. So your initial velocity should just be this vi equals df squared minus 2ab. And also forgot to plug in, substitute our acceleration into this equation here, because we do need to do that, so let's go ahead and do that. So here, and now you have solved your problem. That should get you your initial velocity. Now that we know now that we solved it, without numbers, we can just plug in numbers and solve it. So, the first thing we did here was we determined the net force, and then we determined the net work, because we know that work equals force times the displacement. So we could also, using the work equation right there, this one, that one we can solve for the force, which would be work over displacement. Now, let's plug in our variables to see what we get. calculate our net force. And for that, we remember I said solve for the net force. We use our force of spring equation, which is right here. It should be like should look. So go ahead and try that. So we know that the force of the spring equals negative kx. I'm sorry. Force of oh no, I'm sorry, I made a mistake. We're actually not using the, no, sorry. There is no, this is actually the equation for frictional force here. So we're not actually using this one, we're using the force of a spring, which shouldn't be that, it should be negative kx. There you go, like that. Force of the spring, which is equal to here. Force of spring is negative kx. And you're going to do that for the first spring and the second spring to find your net force. Here, see? So let's go ahead and plug that into Gibbs. We know that force, so we're going to have force of spring 1 plus the force of spring 2 should equal your net force. There you go. So just substituting our force, substituting these two forces with this, you should get negative k1, the coefficient of the first spring plus times the distance plus the second spring times this distance. Distance should be the same, or they're different. And that should give you your force of the total spring force. We know from the problem, we know that the first spring, actually compresses 3.3 meters before it begins to act on the second spring. And it compresses for a total of 0.5 meters, so that means the second spring should be compressed a total of 0.2 meters. So that means for this equation, we're gonna be the first spring is gonna be compressed a total of 0.5 meters because it's gonna be fully compressed throughout the whole time, and spring 2 will only be compressed 0.2 meters since the first string is acting on it for the first 3 meters before it comes to a full stop at the 0.5 meter mark. So let's plug in our numbers. So the force of spring 1 should be 16,000 Newton meters. Negative. It's negative because it's acting in the opposite direction. And it's compressed for 0.5 meters. And you're adding the compression of the second spring, which would be also negative 3,400 Newton meters, times the displacement, which the displacement, the distance, which the distance should be 2.2 meters. And you should get to your force of spring, your net force of spring. Right? There it is. When you solve that, you should get I'm gonna calculator on solve for it. You should get negative 1480 as your net spring force. Newtons. Should be newtons. Once you solve for your net force, you can determine your net work on the whole system using just the work equation, which is just the work times the work equals force times the displacement. See? And then just solve for work. So you're going to be plugging in this quantity for your F, and your displacement is going to be 0.5 meters, because that's the time it takes for the object, the car, to stop. Hold on a second, I did something wrong. Oh, I'm sorry. Yeah, you don't do that yet, actually. You have to solve for the work done. You have to solve for the first. You have to solve for the work done by the first spring on the car, and then you solve for the work done by the second spring on the car. So you're gonna be using this equation right here, work, and for the first equation, you're gonna have, for the first spring you're gonna do this, and the second spring. Now going back to this equation here, this one, you can you know your forces. You're gonna know your net force of the first spring here, and then your net force of the second spring here. So this individual quantity, it should be your force for the first spring, and this individual quantity should be the force for the second spring. There you go. The net force of the spring one, is here, 16,000 meters times half a meter, and the spring of the force of the second spring, which is negative 34 millimeters times 22 meters. You should get, for the first force, the spring 1, you should get negative 800 newtons, and for the force of spring 2, you should get negative 680 newtons. Once you solve for those individual forces, you can solve for the individual works from both the different springs, from the two different springs, using this equation of force. You can solve for your work on each individual spring. So let's go ahead and do that. I'm gonna go ahead and do that for both springs. So when you solve for these two work equations, you should get for the first thing you should get negative 200 joules, and the second you should get negative 68 joules. Right there. So that means that your net work should equal to negative 268 joules. Once you determine your net work, you can actually solve for your force, which actually I messed up because this is actually all wrong here. Oh my god. Alright, so here I messed up. I got it the wrong way. Okay, so using this formula here, we can solve for force. So force would just equal work over displacement. We determined that our net work is negative 268 joules. So we plug that in and divide it by the displacement, which is 0.5 meters. That should give you a force of negative 536 newtons. So now you determine your force and your work. You can find out your acceleration using the second law. You know that means second law is force times the mass times the acceleration. You just solve for the acceleration, which should be the force divided by the mass, right there. And you can substitute that into your kinematic equation. Vf squared equals vi squared plus 2a times the displacement and you know that you're solving for your v initial, so your v initial would be the square root of vf squared minus 2 see, and then just plug in all your numbers and that should get you your answer. Vi equals you know that your initial final velocity is going to be 0 minus 2 times the force, and that force we determine to be negative 200, no, negative 536 joules. Newton's, sorry. Divided by the displacement, which is 0.5 meters. And then multiplied by the distance of 0, so 0.5 meters. Oh no, I'm sorry. You divided by the mass. I'm sorry. So that's 6,000. 6,000 kg times 0.5 meters. So your equation should look like that once you plug in all your values. And that should get you an initial velocity of 0.299 meters per second. There it is. I know this video is filled with mistakes, but please bear with me. I don't have all the technology. Thanks for watching.